Hey, this is a recording for the Toronto School of Foundation Modeling, and this is lecture two, tokens. For those of you who've missed the in-person session, this is for you. Um, let's get right into it. Yeah. So, so this lecture is about tokens and tokenization, byte-pair encoding, and things like that. These are the in-person rules. So if you're watching this, maybe you probably weren't uh, at the in-person session itself. So in lecture one, we talked about tokens like text input, model, and text output. We basically wanted to build a system that understood language. And understanding language means understanding the the construction of how language is made, and that is text. So most of the internet is full of text, and you basically scrape all of that text and you place like a mathematical model, the algorithm which actually makes the predictions in between your input domain and the output domain. And for a system that understands language, so it's obvious that it needs to be text. Your model consumes text and it produces text, and that's how you interact with these LLMs as well. Like ChatGPT, you give it a prompt and it gives you the response back. And in between both of these things is the model. And the modeling choice can be anything. It can be a matrix multiplication. In lecture one, we talked about just linear models and straight lines and planes. And then you can make it n-dimensional, and an n-dimensional extension of that of a linear model as matrix multiplications can be represented as matrix multiplications. And you can have nonlinearities, and there are these things called multi-layer perceptrons, which are basically series of matrix multiplications with some nonlinearities in between to introduce complexity. Anyway, this was all in lecture one, right? And this is for some in-person stuff here. Uh, so what I want to show here is there are some guest lectures, September 16th, if you're watching this before September 16th. Hopefully, you'll show up to the guest lecture on human annotations by Claire. She built the entire annotation pipeline of Cohere from the ground up, and that's going to be a really good lecture. And there are some lecture notes here, uh, like the schedule of the actual lectures, but you can also find them here, tsfm.ca tangents, and that will take you to the actual schedule and up-to-date information. Anyway, so when we talk about text input and a mathematical model that sits in between, and there's a text output, we immediately run into a dissonance here, like something that doesn't make sense. What is that? Text is discrete, text is symbolic, and mathematical models are not actually operating on symbolic data and discrete data. It's operating on continuous data, you know. So when we talked about matrix multiplications, we talked about numbers, how matrix multiplications are operating on these vectors, and these vectors are basically like coordinates in an n-dimensional space. So we want a model that operates in the mathematical domain and uh, somehow transform the input and output domains to be compatible with how we model things, which means bringing text into the realm of numbers. And again, text is discrete. There's nothing in between the letters A and B. In the meantime, like in numbers, you can have between 1 and 2, you have 1.1, 1.2, and between 1 and 1.1, you have 1.001, 1.002, and so on. So text is continuous. There are infinitely many values between that's it in between two numbers. So if text is discrete and we're doing mathematical models that operate in continuous data, how do we bring this into this framework of learning? Um, so the high level answer is that the spirit of machine learning, any machine learning problem that you pick, is that you can learn useful representations and patterns based on data. You observe your data and you predict based on using your mathematical model, and you get a sense of how far you're off from the target because you usually know the ground truth. and sometimes in very smart ways. It's not obvious what the ground truth is sometimes. So most of the work there in that case would go into how can you craft a signal that would act as a proxy for telling me how far off I am from my target. So, and you basically have this, you tune yourself to signal fit the signal, and that is the high level spirit of machine learning. And if we are saying that we can start off by making really bad predictions, and as long as we have a signal and as long as we have the ability to tune ourselves to fit the data better, it an application of that thought process is basically okay, if our text is symbolic or discrete, maybe we can map the alphabet to a vector of numbers. So you can do that here. So the letter A maps to a vector of random numbers, whether letter B maps to a vector of random numbers, and C maps to something else, and so on. So every alphabet in the English language can have its own vector representation, and not just alphabet. It can be punctuation, it can be numbers. So you can basically construct a dictionary which maps your alphabet or like symbolic discrete domain to a bunch of numbers. And you have this dictionary. And initially, you're just allocating these randomly, right? It doesn't really mean anything for A to have this specific vector, or B to have this specific vector, and C to have this specific vector. You can change these out, like swap the values of A with C's values and B's with Z's values, or something like that. And it doesn't mean anything because initially, when we start off with this allocation, it's kind of random. It can be anything. But the idea is that when the model actually sees the numbers that correspond to these characters, and when it sees many, many, many characters over the course of seeing the internet, it receives all this error correction signals and it tunes itself and tunes also these vectors in this dictionary, and then we end up with meaningful representations that this vector at the end of training would look something completely different, because the network is tuning itself so that the vector that represents this alphabet is is actually capturing the meaning in the text. If that makes sense. So this is kind of an incomplete picture of how we can represent text with numbers, and there is also this thing of granularity, right? Why do we have to represent letters with numbers? Why can't we represent words with numbers? Why can't we represent sentences, phrases with numbers? That's the whole field of embeddings. If you've heard of the word text embeddings, that's basically what they're talking about, where an embedding model can embed entire documents into and compress entire documents into a single vector. So there's also the question of what level of granularity do we go with to represent the discrete domain, the text domain, uh, to represent that in terms of vectors. So again, like I said, we have the options of alphabet, words, uh, phrases, sentences, or entire documents. So how do we know that maybe we should go with one of these? How do we evaluate that and how do we think about that? So that's the incomplete picture because we haven't discussed that yet. But the idea is similar. You basically have a dictionary that maps these discrete domain values to vectors of numbers, you know. Um, and before we dive into this any further, let's ask a more fundamental question. And that fundamental question is, how do we even represent text to computers? We are talking about text being discrete, and it's very intuitive to us when we're looking at text that, okay, W is the alphabet W, and like these words have meaning, and when these words come together in a very specific way, we can capture the meaning. But how is text represented to computers? For that, we can actually talk about how is text represented to computers. Okay, so let's see. So how is text represented to computers? Computers work in binary, in bits, right? Each bit can be either a 1 or a 0. So here, each bit, the 1 or 0. So that's the binary representation. So if you wanted to represent the number 0, you would just go with 0. If you want to represent the number 1, you would just go with 1 because that's binary. And if you wanted to represent the number 2, you would go with 1, 0, number 3, 1, 1, and then number 4 is 1, 0, 0, and so on. So there is this thing here, which is you, this binary representation is what computers understand. And the symbolic domain is what we find intuitive of like, okay, this is basically symbol manipulation, characters come together to form words, words come together to form sentences and all of that. So it's the similar spirit we draw from what we just discussed. So we maintain a dictionary that maps these alphabet to binary representations. And in the 1960s, before computers as we know them today were a thing, there were these systems, teleprinters, and all these legacy systems that operated with like I forgot what it's called, like punching tape, um, and like tape-based machines, basically. And before computers were mainstream, we needed some representation of how do we come up with a mapping that maps these alphabets to binary numbers or binary representations. So then in 1960s, there was this thing called ASCII, which was which basically stands for the American Standard for Information Interchange, I think. Let me quickly verify that. American Standard Code for Information Interchange. Yeah. So, American Standard Code for Information Interchange, basically a bunch of people in the 1960s came together and said, like we have 26 alphabet and we have A to Z, and we have uppercase and lowercase. So those are mostly the printable characters in addition to the punctuations, digits, and all of that. So they basically came together to come up with a standardized mapping of this text to binary representations. And what that looked like was 7 bits. They basically allocated 7 bits to represent uh, any character that we would want to use. So there are 95 printable characters in ASCII, and there are 33 control characters. And printable characters, like I said, are like the lowercase, uppercase alphabet, and the digits and the punctuations. Anything you can print on the paper, basically, is a printable character. And there were 95 printable characters. And there were 33 control characters. Control characters are basically almost instructions to the systems that this encoding mechanism would interact with. So it can be like um, an end of file marker or a beginning of file marker, because where an encoding scheme is telling the software that, hey, like this marks the beginning of a file and this marks the ending of a file. So if you see the end of file marker, just don't read anything else, exit that, or close the file stream or something like that. So so 33 control characters and 95 printable characters sum up to 128 uh, characters in total that ASCII actually allocated binary representations for. And 128 characters can be fit in 7 bits. So which is why ASCII is 7 bits. Uh, yeah. And we know that computers work today with bytes. Most computers today are byte addressable, which means the atomic unit of addressing into the memory is like a byte, which is 8 bits instead of 7 bits. So modern computers, when we look at like ASCII, they're actually always prepending the 7 bits with 1 0, you know. So this is basically the representation here, which is you have 0 followed by 7 X marks. That could be the actual ASCII code, and you always have a 1 in front to represent ASCII as a byte. So each character would be 1 byte, but with the most significant bit always being 0. And the 7 bits actually taking the values of the characters, whether that's control characters or printable characters. And what do the actual values look like? They did a smart thing, which was uh, Now they look at the 7 bits, and the seventh bit here is always one for the uppercase, like basically for any characters, like for any alphabet. So they said, okay, the seventh bit is going to be one, and the least significant bit is one for the uppercase alphabet A. And everything's contiguous. Like, so from capital A to capital Z, you basically have continuations of this. So 65, 66, 67, and all the way to, I think, 90. Yeah, 90. Um, so there you have the uppercase alphabet. And so they could have gone on to allocate whatever number 90 is, they could have gone on to allocate the lowercase alphabet. But they wanted to make the distinction between uppercase and lowercase very clear to the humans. Like it should be like human representable. So what they did was for lowercase, they started with 1 1. Instead of directly continuing after the uppercase Z, they assign a bunch of other characters in between the uppercase Z and the lowercase a, so that when the lowercase alphabet starts, it's easy to distinguish between an uppercase alphabet and lowercase alphabet. And how do you distinguish that? It's by looking at the sixth bit. And the sixth bit for all the uppercase alphabet is zeros. And the sixth bit for all the lowercase alphabet is one. So you can just try to read or like get a good sense of whether or not a lowercase alphabet, which lowercase alphabet, and which lowercase, like which uppercase alphabet is being represented by just looking at the binary. And that's like a nice feature. And before ASCII, there were other encoding mechanisms, right? Like if we talk about why we even needed ASCII in the first place, we have these different systems, right? There are maybe one manufacturer came up with their own dictionary, and the second manufacturer, like a competing manufacturer, didn't want to adopt that and came up with their own encoding scheme, like own dictionary that maps these characters to binary. So, which meant that these systems could not work together. If you created something using system one and wanted to share that with system two would read that as something completely different, because to system two, those binary representations actually look like map to completely different alphabet or completely different set of characters. So there was no standardization in place, which meant that systems could not work together. There were all of these issues doing interoperability, and so these are things that caused a headache. And another thing was that this seems quite trivial when we are talking about this, where all the alphabet are contiguous in this dictionary, where like if you start with uppercase A and go all the way to the uppercase Z, you're just like adding one, adding one, adding one to get to the next alphabet. But the other encoding schemes did not actually respect that. They actually, before ASCII, they were maybe A, B, C would be grouped together, but then there's a big break and D, E, F would be somewhere else and letter Z would be somewhere else. So these are discontiguous chunks of alphabet assignments to binary representations, which means if you look at the code, you cannot write code like this. Oh, is the variable greater than the uppercase A and lowercase z? It's actually comparing like the number values of like whether this variable is greater than that number or less than that number. To basically, if you wanted to write code that's checked, okay, is this variable a lowercase alphabet? If you wanted to ask that question, you can write the simple condition where it's basically two equality checks, so inequality checks, and then you just AND them. You could not do that where with encoding schemes that assign discontiguous chunks to different alphabet, which was an issue. And this was such an issue that there was a presidential mandate for all federal systems to use ASCII. That whatever encoding scheme that these federal systems used, like different encoding schemes that these federal systems used, the presidential mandate was to abolish all of them and just for every system to adopt ASCII and to have ASCII as the standard. Because the technology being new, meant that everyone came up with their own systems of using things. Kind of how like the AI landscape is evolving today. Like you have MCPs, and maybe there will be something else that comes after that makes it the standard way to do function calls and tool use. So when a technology is very new, standardization is not in place yet. And that causes a whole bunch of issues in the ecosystem. And like ASCII, when they came up in 1960s, it was a very welcome standardization back then. If you want to know what upper and lowercase y are in ASCII, you can try to figure that out by just looking at the offsets from the initial alphabet, and you'll again see that the only way in which the uppercase alphabet and the lowercase alphabet differ is the sixth significant bit, and which would be a zero for uppercase and one for lowercase. Okay, so we covered ASCII now. And now we're asking the question, how do we support the advent of the internet with an encoding scheme, right? So this was ASCII was in the 1960s, and internet really was developed in the very late 80s, early 90s. So there was a long period for which ASCII was fine. It was working well. But there were some immediate limitations for ASCII, right? And those immediate limitations are that it's only focusing on English. That's the immediate part, like because it's designed with English keywords in mind. You're talking about English alphabet. And what if there was a Japanese system? What if there was like a Korean system and all of these things that ASCII would not work for, because it's 7 bits long, it has 128 values, and everything's taken up. It's fully dense. There's no gaps in where you can fill up new alphabet. So that was an issue. Like we cannot actually support multilingual encoding schemes in a standardized way. Um, and obviously there's no emoji support, but emojis weren't even a thing in the 1960s, so it makes sense that ASCII developers did not come up with it. But there was no future proofing. That was the issue mainly, because you have 127 dedicated things, and you'll have a lot more options than that as the world gets access to computers, and we want systems to work together well. And so clearly there was a need for a new encoding scheme. And and whatever this new encoding scheme would turn out to be, we have to make sure that this encoding scheme would not break legacy systems. There is an immediate solution, right? An immediate solution is to just say, okay, why just stick to 7 bits? If computers are slowly moving towards a byte addressable world where a byte means 8 bits, why can't we just have 8 bits to represent 256 values, right? And people tried that. People tried maintaining extended ASCII. Uh, you can look it up. You can call it extended ASCII, which basically assigns the values for the eighth bit. The eighth bit can either be 0 or 1. In standard ASCII, the eighth bit is always 0. But if you allocated it as 1, then you have like an additional 128 values that you can add to this dictionary. And these 128 values, like an additional 128 values, still won't solve the issue, because like if I'm developing extended ASCII, I would want Telugu characters because Telugu is the language I speak, and I would want Telugu characters to take those 7 bits when the eighth bit is 1. And like different people with different priorities and different system requirements would build their own extended ASCII systems, which again like brought the issue back of like non-standardized extended ASCII system, where like there are systems that are using extended ASCII, but these are using different notions of extended ASCII. So you can say, okay, if 8 bits is still limiting, why not just allocate 16 bits or 32 bits or even more? And and of course, this has disastrous implications for text that is already encoded efficiently. Like if I developed a scheme that says, okay, each character now takes 16 bits instead of 7 bits, like traditional ASCII, I cannot go up to someone that only like I cannot go up to a publisher, that's publishing English books and say, hey, like, so I have this new encoding scheme that's 2x expensive, that's twice as expensive, but I want you to take it up because it's useful for the rest of the world. Arguments like this would never work in the real world because no one wants to sacrifice efficiency knowing that, oh, this is going to help someone else, you know? Uh, and obviously, like computers, as they were becoming a thing, just naively allocating more bits to representing text would just mean your software becomes slower, your files become larger, And these are not very powerful computers we are talking about, right? We are talking about the very beginning of the computer revolution. So, and if there's a proposal to say, oh, everything's twice as words now, it's just not going to sell. No one's going to actually adopt that encoding scheme. So, which means there needs to be a better solution. Um, and that brings us to Unicode. So, so the core motivation of Unicode was to develop an encoding scheme that is backwards compatible and is also 8 bits. Like we'll get into what that 8 bits means, but it's not technically strictly 8 bits. But their core motivation was to develop an encoding scheme that is future proof, that like it's not just about what characters do we want to represent today, but it's also about what characters might we want to represent in the future, maybe a decade from now, maybe 15 years from now, maybe even 2 years from now. So they wanted to develop, just the Unicode consortium came together uh, in the 1990s to basically build an encoding scheme that is backwards compatible, future proof. Yeah, so their primary thesis or like approach was that any character that does not fit in a single byte should be represented as a sequence of bytes, which means what characters don't fit in a single byte? These are characters that are not ASCII. You know, if if you're not representing ASCII text, then that character would take up multiple bytes, which is like 1 byte or 2 bytes, sorry, which is 2 bytes, 3 bytes, and all the way up to 4 bytes as well. Which means English documents would still occupy a byte per character. Yeah. And any byte starting with zero, because we looked at it here, um, any byte starting with zero here as the most significant bit, like the eighth bit, is ASCII. And Unicode still sticks to that. So if you encode English text to Unicode, and which is like UTF-8 specifically, you'll see that any English character text or simple punctuations just take the form of 0 and 7 bits that represent the actual thing. You can actually verify this. We can look at the Python console and look at the binary representations of text. But let's look at that. Okay. We can say, okay. So we can say maybe, hi, this is TSFM. So this is the string that I want to encode. Maybe let me zoom in here. Hi, this is TSFM. That's the text I want to encode. And I can just say dot encode UTF-8. And this is basically like the UTF-8 encoding. And the B prefix here is basically just talking about it being like the binary representation. And you can actually look at the bytes here. Uh, why is that list? If you look at the list, these are the number representations of that. And you can actually look at also. Let's just look at bytes. Um, bytes of 0 is 104, and you can represent that as, yeah. So this is 110. This is the first bit is always 0 here. So you can say 1100, 1101, 000. That's the letter H. And for I, that would be bin of bytes 1. So that's 110, 1001, with the eighth bit being 0. And you can even see how Unicode maps the non-English characters to 2 bytes. Like if I see, uh, whereas hi, this is TSFM. So if I compute the number of characters in this, let's just assign this TSFM. So if I say length of TSFM, it has 16 characters, right? And if I'm saying that each character maps to 1 byte, the number of characters in this text should be equal to the number of bytes that are in this text as well, which we can confirm by looking at length of bytes, 16. So clearly, even UTF-8, if you have just English text, it maps each character to the ASCII form of it using 1 byte each. So how many ever characters there are is how many ever bytes there are in UTF-8, just for if you're using English with some simple punctuations. But anytime you don't use English, let's say you have an emoji string, which would be, maybe we can use what emoji should we use? This, right? So emoji dot encode of UTF-8. So if you look at this length, so a single emoji now doesn't take just 1 byte, but 4 bytes, because anything that doesn't fall in the normal ASCII range, Unicode represents it as a sequence of multiple bytes. We can try to understand what that sequence of multiple bytes actually looks like and what Unicode format is, which we'll do right now. Okay, so this is the basic form of Unicode, which is that anything that is an ASCII is still, starting with 0, and you have 7 payload bits. So still a single byte, and you're representing most English text. And anything else has this beginning of 110. And the way to look at it is you look at this byte, this 110 with 5 other x's here. So you count the number of ones in between the first one and the first 0 in this byte. So how many ones are there in between the first one and first 0? It's 1, which means it's telling us that there's one more byte after this to decode this successfully. So, and any continuation byte is represented as 1 0 followed by a certain number of bits. So 6 bits here. So the total number of bits that we are allocating to representing this text is 6 plus 5, 11 payload bits. So that 11-bit string is what encodes uh, any text, like that fits in that. So you're allocating 11 bits to that. So two byte representations are more. We'll talk about like how it's split between 1 byte, 2 bytes, 3 bytes, and 4 bytes, but that's the idea. And for 3 bytes, so you're basically counting again the number of ones in between the first one and the first 0. You have 2, which is basically saying that there are 2 more bytes coming after this for a successful decoding of whatever this character turns out to be. So again, there are 2 continuation bytes now. So both of these start with 1, 1, 0, and they come with their own like representation. And this X is basically a placeholder for what the actual bits would be. And for 4 byte form, again, I think this is obvious. There are 3 ones in between the first one and the first 0, which is basically telling us that there are 3 more bytes after this, the continuation bytes, all of them that start with 1, 0. And putting all these X's together gives us 21 payload bits. 21 bits is quite a lot. So you can actually compute 2 power 21. That's like 2 million. 2 power 21 is like 2,097,152. So that's a lot of representational power baked into Unicode. So you can represent many, many, many characters. And today, Unicode actually assigns has mappings from around 100 for around 150,000 characters. So that's what Unicode is. And there is a deep dive section here, uh, right? Uh, there's this thing called basic multilingual plane. And the basic multilingual plane consists of most often used characters. If the uh, basically any multilingual text, we would want for it to not be 4 bytes, because multilinguality is like a universal concept where we want computers to be still efficient, if not for 1 byte, most of language that we want to use in like a regular day and like most popular communication strings should be efficiently encoded. So that when you decode or like when you encode like a particular string using or particular character using UTF-8, you don't want it to always decode to like 4 bytes, so you want it to be efficient. So the basic multilingual plane captures, I think, uh, like many like morphological variations of characters and some other languages as well. Uh, the you can Google it, you can understand what how Unicode actually assigns these things. And yeah, and there are these things called supplementary planes. And so you have 21 bits here, and so that's the maximum capacity for UTF-8, right? Where you basically have 4 bytes that represents a specific character. And these 4 bytes, some of these are hard coded, which are the headers for the continuation bytes, which always start with 10. So a byte can only really represent 6 bits here. So if you sum up all of these, they sum up to 21 payload bits, and that's the maximum capacity for Unicode. Uh, and that's plenty. Like how many? Like I don't think it's very realistic to have like 2 million characters. Anyway, so these 21 bits are actually broken into two parts. The first 5 bits represent the planes, like the basic multilingual plane, and there are supplementary planes that specialize in different languages or different variations and emojis and all of that. So the basic multilingual plane has the first 5 bits as zeros. So the first 5 bits are always zeros in basic multilingual plane. And the second 16 bits is basically representing the position within that multilingual plane, like within that basic multilingual plane, what position are we trying to denote is what it describes. Um, Hopefully you have the link to this canvas and you can read more about the supplementary planes. You can Google how Unicode actually assigns these things, how many assignments there are, the variations of Unicode, because Unicode also has versions, because we are constantly coming up with new emojis, new scripts being incorporated into the scheme. So there's Unicode. I don't know what version we are at right now, but there are versions as well. So you can look at what version each character was introduced and how does Unicode actually how do Unicode updates get propagated throughout the internet. So you can read all of these cool things on your own time, but it's interesting to find out the scheme that we've settled on today because all of internet now uses Unicode like UTF-8, and it's always fun to learn about how text is represented to computers because as we'll see the thing that we just learned here would make sense. Like that's like the byte representations of text is what we will be working with to construct a better representation uh, for the dictionary that we talked about. Or do we want to represent a dictionary in terms of like letters, um, or like numbers, sorry, letters or words or phrases or sentences, and we'll have an algorithm that basically deals with bytes and constructs a level of granularity that we would be happy with. And if you've ever trained a language model, or if you've used a bad language model where like the weights are maybe messed up, you did a bad job restoring the weights, maybe you're just starting out with random initialization, and you're trying this LLM to basically get it to generate some text. At the tokenizer level, maybe you've seen this issue of like, oh, this is not a valid token because this byte string is invalid. Because Unicode sticks to this format, let's say you have 1110 here. Let me zoom here. Yeah. Let's say you have 1110 here, and all the continuation bytes have to start with 10. That's a rule. So if your continuation byte, let's say, because your LLM can actually, uh, it views each byte as a token as well, it can technically predict that, oh, the next byte is starting with 11. And that's an invalid byte. Like UTF-8 would look at that and say, this is not a valid string because a continuation byte has to start with the 2 bytes 10, 2 bits 10. And if it's 11, it just means that it's an invalid bit or like an invalid continuation, invalid string. So if you've worked with random language models and you were trying to sample from them and like using tokenizers to decode it, maybe you've seen this issue pop up that it's not an invalid byte to decode from. Sorry, that it is an invalid byte to decode from, and that's the issue because Unicode has its own set of rules for what makes a valid string and what doesn't, and we'll have to respect those rules. And in a way, like the language model also knows because it has seen very similar patterns across all of the internet where they respect this rule of how text translates to bytes. Trained language models actually never, mm, almost never predict. Uh, an invalid byte because those are patterns that stray far from what we have seen in training data. Because training data is all like valid UTF-8 encodings. So there is no way an invalid UTF-8 creeps into your training because you filter for that. You filter that out. Anything that seems broken. Okay. Um, so we have it here. We have the Unicode, we talked about Unicode, how is text represented to models, to computers. We talked about ASCII and how standardization was such a big issue that there was a presidential mandate for all federal systems to use ASCII and the evolution of Unicode from ASCII. And Unicode was actually developed, I don't know if you know this company called Xerox Research. They were popular for, they became popularized for Xerox machines, obviously. But more importantly, Xerox research in Palo Alto had many, many contributions to internet. It was where object-oriented programming was developed. It was where GUIs were developed, like the graphical user interface. And there's the story about Microsoft and Apple both stealing graphical user interfaces from Xerox research in Palo Alto. So interesting stories behind like the development of Unicode as well. Like Unicode specifically was developed by people both at Apple and Xerox Research through a collaboration. Uh, so if you're interested, you can read more about this. But this is fun too. This was a fun segue into how computers represent text, or rather, how text is represented to computers. Okay, so now we get back to the question that we had at hand. How do we represent the text to the model, right? So there are different alternatives here. And by how do we represent text to the model, or by asking that question, I really mean this dictionary that we talked about. What is this? We have the question of what level of granularity do we represent this in? Whether that's characters or letters or like characters or words or subwords or bytes or sentences or entire documents. So we need to decide on that. And we have a bunch of options with us. So let's just look at what the options are and what we would want to look at. So if we wanted to use characters to represent text to the model, we can follow UTF-8 encoding, which is a standard across the web. There are 144,000 valid characters in UTF-8 today, maybe even more. And UTF-8 has the capacity to accommodate, like a million characters. So why can't we stick to the level of granularity of doing characters? And the answer is that we can. We absolutely can represent the dictionary and construct the dictionary that maps characters to vectors. But there is a problem here, especially like when you're looking at from a system perspective, is that you have a huge vocabulary, which is 144,000 unique characters. But every sentence would also need to expand the number of characters, right? We will, so this will become clearer later on when we talk about, okay, like how many characters uh, does a sentence have? And if it has, like, when we talk about a million context length, all of these LLM providers, you see them releasing stuff saying, oh, there's a 256,000 context length or 1 million context length. And a token, so they're talking about tokens. And we'll get to what tokens means, but token is roughly 4 characters. So you're basically, by choosing to go with characters, you're expanding the context length requirements by 4 times. So if you wanted the same 256,000 token uh, context length in a large language model, that 256,000 here now would mean 1 million, you know. So this 1 million sequence length is, again, it's hard. This is Those systems are hard to build because of memory requirements of of scaling context, and the context is also quadratic um, in complexity. So in the attention mechanism, all of this we'll get to later, but there is a real cost to just using characters as the base vocabulary in LLMs. And the other option is that we can use words. But the issue with words is like more perhaps like apparent, which is it's great, but the coverage is low. What if you make a typo? You know, and if we make typos that we don't recognize, then all of them get mapped to something unknown. So because like our dictionary then would not just be a mapping of words like, oh, there's cow, there is eyes, there is banana or something. And in the end, we'll also have an element for an unknown word that'll have like a corresponding embedding. Because like if we see unknown words, which is very realistic, because a user can make a typo and can just like make up word or forget punctuation, forget space, and all of these things. So then we would basically like encode that to like unknown token. So this one unknown word would get overloaded using like any mistake would get mapped to the key of unknown in this dictionary, and that's not ideal. And across languages, across meanings and morphological variations, there are a lot of words, so the coverage is low, even if semantically, like, it makes sense that the atomic unit for us to construct a dictionary, could be words. Like, it makes sense because each word carries its own meaning, and it's really intuitive when we talk about transformers as modeling relationships between words to form sentences and stuff. So yeah, words are great, but coverage is low. And there's an example here of ByteDance. If before ByteDance was a company, if you asked like maybe a language model built on words, what is ByteDance? It wouldn't work because the word ByteDance would get mapped to an unknown word. So it has no notion that it's actually made up of two distinct concepts, byte and dance. Um, and then maybe you can posit that maybe it's a technology company because it's talking about dancing bytes. Uh, so all of these issues with using like words, not just that there are a lot of words we cannot capture, and it keeps changing with the culture itself, uh, and that it's very prone to errors and bytes. So we talked about issues with characters, right? Characters are like the decode to many tokens, or like many it's inefficient. Your system becomes very prohibitively expensive to train if you stick to character-based training. Um, okay, so here, let's consider this following text. This is the acceptance email that I sent out for TSFM, and this is the English version of that, and there is a Telugu translation. This is not very accurate Telugu translation because I just passed it through ChatGPT, and for some reason it inserted some Hindi as well, like a different language, Taki. But anyway, this is like the same piece of text semantically in both English and Telugu. And if we look at the number of characters that this text has, it is 1,284 characters. Um, and if you look at the number of bytes by encoding this to UTF-8, we observe that there are 1,323 bytes. And 1,323 bytes is not bad. It's very, it's more because this piece of text is mostly English and punctuations. It makes sense that each character is just one byte, but there's a bunch of uncommon punctuation, like an arrow mark here that is not just a combination of a hyphen and a greater than symbol, and there's like an emoji here, and a bunch of things like that. So this maps to multiple bytes, right? So, which is why we don't see just 1284 bytes in this piece of text, because there are bytes, there are punctuations and markers that are used in this text that decode to uh, more than 1 byte per character. So in the end, we end up with 1323 bytes, so which is even more inefficient than just using characters. And we talked about us requiring, uh, like we need to be mindful of the system level considerations before we build our model and decide on the granularity of the dictionary that we want to construct. And at the same time, we can actually look at what LLMs do today using tokenization. And we'll get into what that means specifically. But what it's doing here is that if we tokenize this piece of text, it's mapping to only 315 tokens. That's almost like a 4 times improvement over what we've seen in just like the character and the byte representations of this piece of text. And tokens, as you can see, each token is taking a different color here. So great is 1 token, space news is 1 token, the exclamation mark is 1 token, space I am is 1 token, space excited is 1 token, and so on. So you have all of these tokens that you can kind of just identify based on the color here. So the total number of tokens here is 315. And a way to maybe say that, like, okay, um, this makes sense because like you're grouping these words in a very specific way. It's either subwords or combination of two words. And how do we figure these groupings out is what we're going to look at right now. But on the flip side, we can also look at Telugu text, right? So this is the Telugu text. And you can look at the fact that it maps to this piece of text contains 1463 characters. And how many bytes does it have? This has 3626 bytes. And this is for this Telugu text, we observe around 2.4 bytes per character. So it's no longer just 1 byte per character uh, constraint. We're actually even making it worse by stretching out each character into 2 bytes. Because, like we talked about Unicode, Unicode reserves 1 byte representations for mostly ASCII. So anything that is not ASCII, like Telugu text here and emojis here, and like special markers and punctuations, those map to 2 bytes and sometimes 4 bytes even. Like all the emojis map to 4 bytes, and some Telugu text maps to 2 bytes. So so it averages out to around 2.4 bytes per character. So this is even worse when we're talking about like system level requirements. And then we can talk about token count and run this piece of text through the same tokenization scheme. And then we find out that there are 591 tokens, which is still worse than, you know, the token count in the English text, but it also has more characters, right? Like the English has like 1284 characters, and the Telugu version has 1463 characters. So it has more number of characters, but the token count is also very reasonable. It's only 591 tokens, which is, for in terms of bytes, it's a huge improvement. It's almost a 6 times improvement. And for characters, it's I think 2.5 times improvement. So clearly there is a better way to go about this. And what we see here uh, is that the bytes is definitely prohibitively expensive. We can represent every possible text with as a sequence of bytes, but it is just that it will turn out to be even more expensive than characters. So we want to basically do something smarter that's going to be friendly to the system that we want to work with. And that is basically tokenization, where a token is like subword representations. Maybe it's not just like one word, it can be less than a word, or it can be more than a word by grouping two very frequent words together. And the way tokenization works is this. And we are specifically looking at the byte-pair encoding algorithm, you know, and and we are basically asking the question of like, okay, so this is So we just discussed the issues with just doing from a bytes perspective. It's just so many bytes that we wouldn't uh, be able to represent and cost effectively train the system. So we need to go a level deeper that is both efficient and can represent all possibilities of the output space. We don't want to run into the flaws of the other schemes that we discussed. Oh, words are good, but the coverage is low. There's too much error-prone behavior in there because someone makes a typo, someone forgets a space, and all of these things. So we want to solve all of these issues while designing uh, a cost-efficient way to represent the dictionary that we want to construct, right? So, and that brings us to byte pair encoding. So the intuition is very simple. You take a corpus of data. For example, it can be the Harry Potter books, it can be the code from a GitHub repo, and then you compute the most frequent occurrence of a pair of bytes. That is what uh, we're going to do. So every text, every piece of text, every corpus can be represented as a sequence of bytes. Uh, just like how we looked at based on the Unicode representation, where each character is basically a sequence of bytes. It's either one byte or a sequence of bytes. And then the algorithm basically like we look at, okay, what is the pair of bytes that is the most frequent? And we look at those pair of bytes and we just merge this and call it a new token. And we express our same corpus, whether that's Harry Potter or like a code, uh, like a code repo, in we express that in terms of this new token, you know. And then we'll actually look at a visualization for this that'll make things clearer. Uh, but and then we record the merge, we add the new token to our vocabulary, and we just repeat the steps. We repeat these steps 1 to 5 here. So we start with you compute the most frequent pair, you merge this pair, you express the corpus in terms of new token, and you record the merge, add the token to a new vocabulary, and all of that. This looks fine, like this seems fine. Well, like the core intuition is that we're looking for patterns we can compress. That's basically how all compression algorithms work too. It's looking at like, okay, what is the most frequent group of things that I can find and merge together and actually, uh, call it like a unified thing. Basically, you're constructing new symbols that are groupings of other symbols that occur together very frequently. And we can take a look at a visualization that actually, makes it clearer what byte pair encoding is actually doing. So this is tsfm.ca/lecture2. The password is, you can actually see this, tsfm.ca lecture2, and I can zoom this here. And the password is TOKENS. That's the password. T space O space, sorry, T comma O comma K comma E comma N comma S. So tokens where each letter is separated by a comma. That's the password to tsfm.ca lecture 2. And let's write a new piece of text here. Toronto, Toronto, Toronto. I'm teaching at the Toronto School of Foundation Modeling. Then maybe you can say, repeat this. It's almost like a banner. Okay, so let's look at what's happening here. And one thing I forgot to mention here is there's this thing called pre-tokenization. And what is pre-tokenization? Uh, there's an issue that almost immediately stands out if we were to do this algorithm kind of naively, you know. Uh, and the issue would be that your your corpus here is just like the Harry Potter books or code from a GitHub repo, and which by themselves are like huge. But we're talking about large scale training, which is like you're scraping the entire internet and you're running this algorithm over that huge corpus. And the thing that we don't want to do is, these steps 1 to 3, like 1 and 3, are very expensive. Like you're basically constructing a frequency table across the entire corpus that could be like terabytes of data. And if you're looking at that and constructing a frequency table, and then you're merging the most frequent tokens or bytes together and calling it a new token, and then you have to express this corpus of like which is terabytes in terms of this new token. This is not great, right? Because it's just too expensive for us to run multiple iterations of this algorithm, and we ideally want to run around maybe like 50,000 iterations of this, or sometimes even 200,000 iterations of this, like how many ever tokens we want out of this algorithm. So to run 50,000 or 200,000 iterations over this terabytes corpus is like insane. So we want to make an optimization, and that optimization is basically pre-tokens. So we talked about like the word-based encoding uh, in terms of constructing the dictionaries. The spirit is similar. So you basically pre-tokenization means that you split your string on a white based on white space, So you can look at this sentence here that says we need to go a level deeper that is both efficient and can represent all possibilities of the output space. You can split this on white space, and it corresponds to a series of tokens called we need to go a level deeper and all of these like other words. So what this tells us by doing this pre-tokenization, we call these pre-tokens when we actually split the string on a white space and count the number of unique occurrences of a certain thing. You know, so I can do this here where I am happy. So if you do pre-tokenization and you're splitting on like white space, you'll have the words I am happy. There's happy here and then there's happy here. Yeah. So this occurs one time, sorry, two times, and this occurs two times. This occurs uh, one time. This occurs one time. So this is the pre-tokenization count that you would construct. So what this basically gives you, the kind of optimization it gives you is that if you encounter the byte A and M, the bytes A and M, the bytes that correspond to A and M, it's already telling you that it occurs two times. And I can say, uh, actually, this is like not super happy. Sorry, not super happy. Yeah. So here, then you have again like not and super, which are both occurring twice. Uh, so when you look at like when you iterate over what bytes there are in these pre-tokens, in this list of pre-tokens, which again correspond to the number of times they occur in this corpus, if you look at the letters S and U and you're trying to compute, okay, how many times do the bytes that correspond to S and U occur together? It's already giving you the answer here, which is two, right? Because super super occur the pre-token super occurs twice. So which means every pair of bytes that makes up this word super also occurs two times. So you're basically pre-computing a frequency corpus, which is basically telling you some information about certain byte pairs. Or like, oh, this byte pair occurs two times, this byte pair occurs three times. So this is an optimization which will allow us to iterate not on the entire corpus, but only on the entire pre-token corpus. And pre-tokens can just be the number of unique words in the corpus that we are iterating over. And when you're operating at a scale of internet, even this pre-token corpus can be huge, but it's still significantly like orders of magnitude smaller than the size of your corpus, which makes it easier for us to iterate over the byte pairs in the pre-tokens uh, here and correspond and compute the occurrence of them independently. Okay, so this is what we have here. I typed out this text: Toronto, Toronto, Toronto. I'm teaching at the Toronto School of Foundation Modeling. Toronto, Toronto, Toronto. Okay, so this is a tokenized preview. Right now, everything is like a separate character or a byte, right? T is a separate byte, O is a separate byte, R is a separate byte, and so on. Um, so it views it as such. Like right now, we initialize our vocabulary with just the number of, with just the bytes that are possible with 8 bits. You can see that here. To 128, we'll see like almost ASCII. So 0 to 127. So 127 is the delete key. 126 is the home. I forget the tilde, I think. And 123 is the flower braces and whatever, and the curly braces. So, and 0 is just null. So you can see what we initialize our vocabulary with, which is 8 bits. So everything in those 8 bits, which is 256 possibilities. So our vocabulary has 256 tokens already. And now everything after that is an optimization. So in this, we have actually pre-tokenized vocabulary. Let's look at the pre-tokens we have. We have the pre-token am, we have the pre-token at, we have the pre-token foundation, we have the pre-token I, and modeling, of, school, teaching, the, Toronto, and Toronto all caps, and all of these. So what this is telling us is like the list of pre-tokens is this. So we basically want to iterate over the pairs of bytes in this pre-tokenized vocabulary. And what we find out is that the adjacent pair frequencies, T and O, occur the most frequently together, which makes sense because I say Toronto, the word Toronto in uppercase, 6 times here. So it makes sense that the pair, I mean, like in each occurrence of Toronto, there are two TO pairs. TO here, TO here. So, which means that because there are 6 occurrences of Toronto, there are 12 occurrences of this pair, of this specific pair, T and O. And then what we do is we step over the algorithm, which basically does what? It merges these 2 tokens or these 2 bytes, TO, and then the expression of the corpus in the pre-tokens changes. Because right now, when we look at the Toronto, the uppercase Toronto, we see the bytes T, O, R, O, and T, O occur separately entirely here. But if we are saying that the algorithm actually merges 2 bytes and assigns it a new identity, we'll see what happens here. So we step through the algorithm, and now TO is 1 token. You know, it's like a unique identity here. You can see it here. TO is a unique identity. And you can look at the merge rules. Merge rules is basically an ordered list of what bytes are you merging together to create a new byte or like to create a new possibility. And if you look at the vocabulary, now initially we had only 256 possibilities because it's zero indexed. 255 was the last one, and now we add a new thing which says, okay, 256th one is TO, which is a sequence of these bytes. And Toronto now is expressed not as just TORONTO, it is expressed as this new identity, which is byte number, which is vocabulary token number 256, which corresponds to TO, and then it's re-expresses that. So it says 256th token, 82nd token, 79th token, 78th token, and 256th token again. So it's like one unique identity. And now let's look at what's next for like the adjacent pair frequencies. And again, we used the word Toronto so many times that the algorithm picks up on that because now it says, oh, this 256th ID occurs with 82nd ID R 6 times because That's how many times it occurs. Uh, and then we step the algorithm, and then now you see the live tokenized preview of this text, which says TOR is like one unique symbol. They're grouped together. And you can see the corpus after merges, which is TOR is one token, O is one token, N is one token, TO is one token. And we probably added a new token here, which is 257 TOR. So our vocabulary size increased by 2 because we ran through the algorithm twice so far. And we can keep running this, and it slowly like computes the adjacent pair frequencies. Uh, so you can see how we ran through multiple times here, and now Toronto becomes a single token because it has said so much in this piece of text. And remember that we will actually be operating at a much larger scale because we'll be operating on the entire web corpus. So we are not actually biasing the algorithm towards something as niche as this, but we're kind of trying to diversify our text options so that we actually pick up on real token frequencies and how tokens are used, how bytes are used in the real world. So we are computing statistics, frequency statistics from the real world. And so you have the vocabulary that's expanded. Now TOR is one token, TORO is one token, Toron is one token, Toronto is one token. And you can see how, like, because this is mostly English text, you can see kind of the suffixes of common things appear to be, and prepositions appear to be one token because it's trying to make this representation more and more efficient, right? Uh, yeah, it's trying to make this representation more efficient. So it makes sense that if we're dealing with tokenization of mostly English text, all the prepositions kind of group together to form one token. All the common suffixes of words that describe action group together to form one token, etc. So that is how BPE works. It starts with a corpus, it pre-tokenizes the corpus for efficiency, and does the frequency counts. And then you look at the pairs of bytes across all the pre-tokens that you have and compute the most occurring byte pair. You merge that and make it into a new identity. And this is the corpus after merges. Um, and you re-express your corpus in terms of the new token that you add. And you're documenting what pair is being merged into a new ID here, these merge rules. And this order of merge rules is actually very important. You need to encode your string. When you actually create a tokenizer and you're trying to encode a string, like a string from the internet or a document, you need to merge in the same order as the merge rules appear. And that's an exercise for you to think about why that is the case. Why is the order of merge rules important? What if you just like flip between the orders and you don't respect the order? What kind of effect does it have? Uh, you can think about that. But this is we do document merge rules, the order of the merge rules for a reason. Uh, so that's byte-pair encoding. And this would bring us to almost the end of the session, which is where I would give you the assignment. And if you have link to the space, you have the GitHub link here, like in the corner. Um, you can't see it right now, but you should probably have link to the space. If you don't have a link to the space, DM me on Slack or Twitter. I can send you the link. But there is an assignment, and I would like you to do the assignment. And there's a whole bunch of interesting things that happen, like with tokenizations when you're doing like byte-pair encoding and you're looking at subword representations. Uh, there are some predictable weirdnesses in tokenization. There's a reason why uh, you know LLMs cannot do math properly. So you can do tick tokenizer, uh, tick tokenizer. Okay, something awesome here. So this is like tick tokenizer, which is you can try the GPT-4 tokenization, or you can even try something actually older. Let's see. GPT. So let's say 23 plus 4467 plus 324. 1, 2, 3, 4, 5, 6. So a lot of people, criticize LLMs for not being able to do simple arithmetic or counting alphabet in words. That's kind of our fault in how we designed them, because to an LLM, the atomic unit of representation is not characters, it's not just numbers, it's not digits, it is tokens. And a token can be anything, it can be a grouping of words. So if you look at how one of OpenAI's earlier models actually tokenized this piece of text, just 23 plus 467 plus 324 plus 1, 2, 3, 4, 5, 6. So 123,456. So 23 is one token here. It's not 2 and 3 being one token. 23 is one token. And 467 is one token. 324 is one token. And 123 is one token. 456 is one token. Which is so weird. Who thinks about addition? Because that's what we're basically doing. We're splitting up the numbers into these different identities, even though it doesn't make intuitive sense to us to split up 123,456 into two distinct components. Why are we doing that? So we are basically like making the LLM's job harder, because how would you operate arithmetic on this? You know, when you're viewing 23 and you don't have a sense of, okay, 2 is the most significant digit here, and 3 is the least significant digit here in terms of what places it is at, the decimal place. And so it has no notion of that. It has no notion that 2 and 3 may come to make 23, because 23 is just one token. So that's the atomic unit that it sees. Even though to you and me, it's so intuitive that 23 is like 2 and 3 uh, next to each other. So it's 20 plus 3, 2 times 10 plus 3. And it has no notion of that. It has to pick up all of that and try to piece together how arithmetic works in this tokenized world, which is, not great. Um, and so no wonder LLMs are bad at arithmetic. And people have tried to do like solutions for this. So here, if you see, I think the E model, yeah, they tokenize by digits. Two is one token. Every number is basically forcibly tokenized as a series of digits, and not just, numbers, not just like distinct chunks of multiple digits for some reason. And clearly it demonstrates, like, there are some empirical results and a lot of papers that study, okay, you do digit-wise tokenization, your arithmetic performance actually improves. It improves by a lot. And that makes sense. And you can even do, like, you might have heard of the prompt, how many letters, how many R's are in the word strawberry, berry. So strawberry here is just one unique token. It's not viewing strawberry as like, oh, strawberry is one strawberry is like a series of letters, STRAUBREBERRY, but it views us as this unique identity that is not composed of anything. Because when I say tokens are atomic, that's what I mean. Even though it's very hard for us to step out of that mindset and say, hey, like, these are this way. For to the model, these are atomic units. These are independent, unique identities. So it's no wonder it is hard that for LLMs to do like this kind of character level manipulations or arithmetic and all of that, because of how we choose to tokenize stuff, the subword, multi-word representations that we are constructing, which are not very natural, just to be efficient in terms of like system level design. Um, and there are more cool things you can do with this, with BPE. Yeah. There's this famous phenomenon of solid gold magic harp, where this seems to be a magical token where you inject that, where if you say this token to an LLM, for some reason it doesn't recognize the token at all. And this kind of happens when the corpus that you trained on for your byte-pair encoding is different from the corpus you trained on for the actual language model training, for actual transformer training. It causes some interesting behavior, which I won't get into here, but you can open this blog and check it out and try to get a sense of all the weirdnesses that come with byte-pair encoding and divergence issues. And then there's another thing, which is, we looked at the thing here, the order of merge list, and this is just English text. And you can look at Harry Potter TXT. So this is the Harry Potter TX, like in text format. It's huge, but let's just copy a part of that, right? Let's copy these and paste it here. Reset it. And now the algorithm runs. You step through it a bunch of times. It's a bit slow because I think I pasted too much text. It seems to be a little bit stuck here. Okay. Anyway, so we did a bunch of steps here on the Harry Potter text, and you can see what appears first here. Like obviously these merge rules are telling us which letters are combined, but it's looking at like the word he is tokenized, is grouped together as the first token because he like probably refers to Harry Potter and the book is about Harry Potter and he comes up in the and he all of that. And there's prepositions all over the place in and the on and there are like suffix things. Uh, er, ar, ed, like things that you attach to a verb usually. Um, so there's a specific pattern that you see here. There's like a and like a conjunction. So there's a specific pattern to the order in which tokens are grouped together. And especially for English language text, you'll see that the things that get merged first are like prepositions or like pronouns and stuff like that. But if you went with code instead, uh, just say flash attention. You can copy this code, or maybe you can just like, I don't want the doc string here. Okay. I mean, there is a doc string still, but we can reset that. Delete this, paste the code. We're splitting on white space, which is not ideal, but we can run through the algorithm a bunch of times. And we'll see that the first thing that gets merged is ST, I mean ON, yeah, but RI, SE. These are not common suffixes. And you'll probably see some underscores as well, like basically the syntax of the language. If you do, yeah, see, N underscore, S underscore, TL dot. So all of these things that you wouldn't normally see in like English language would show up here. And that's just, so the order in which vocabulary is inserted and tokens are merged is actually telling us something about the corpus itself. Like if your LLM or the BPE was trained mostly on code, then you would see that in the merge rules and the order in which vocabulary, like new tokens are assigned in the vocabulary. So you can kind of reverse engineer the compositions of the data mixtures for all of these LLMs by looking at merge rules and vocabularies. And tokenizers for most LLM providers, maybe all of LLM providers, are open sourced. All tokenizers come with merge rule lists, what are the vocabularies, what is the order in which new tokens were inserted. So that you can actually study for whether that's Claude or ChatGPT, Command, all of these models. So a paper went a step further here, a Europe's paper called Reverse Engineering Data Mixture, like data mixture inference attack. So it's basically looking at these tokenizers, the BP tokenizer information, and kind of reverse engineering and finding out, okay, what is the most likely data mixture that this BP tokenizer was trained on? Because people usually reuse the same corpus to train the models also. So just an interesting artifact or like side effect of doing a byte-pair encoding. So that's all about tokens. The assignment again can be found on the canvas. Just go to the right-hand corner in the canvas and you'll see the assignment link, which basically gets you to write and train your own byte-pair encoding tokenizer. And and this is basically tokenization in LLMs and all of the weirdnesses that it comes with, and inefficiencies that it comes with, and it skews the models towards certain behaviors, which are some of them are documented here. So yeah, thank you for listening.